So in last lecture, we started the discussion on the first law of thermodynamics, right? So we started with the application, basically the statement of the first law of thermodynamics, that is energy can neither be created nor be destroyed, right? And it can be converted from one form to another form, right? So we talked about how the first law is applied for a closed system undergoing a cycle. Then we discussed the Joule's experiment, and we talked about how work is completely converted into the heat, right? Then we learned how to apply the first law for a closed system undergoing a change of state. Then we introduced the concept of energy, and we also proved that energy is property of the system, right? Then we talked about what this total energy capital E is made up of. So we said that it is basically made up of the macroscopic form of energy and microscopic form of energy, right? Then we introduced the concept of internal energy. We noted down the symbol used for internal energy will be the capital U, right? And specific internal energy will be designated by small u. Then we talked about the concept of specific heat at constant volume. Then the enthalpy, we introduced the term enthalpy. We talked about what is total enthalpy and specific enthalpy. We also talked about what is the specific heat at constant pressure, right? And at last, we applied the first law for an isolated system, and we made a statement that for an isolated system, the energy of an isolated system remains constant, right? We also talked about what is the ppm1, which is actually the violation of the first law of thermodynamics, right? And at last, we talked about the limitations of the first law of thermodynamics, and why only first law of thermodynamics is not sufficient to analyze the situation or analyze the problem in the thermodynamics. So we have to have the second law of thermodynamics, right? So that is what we concluded in the last lecture. Now moving further in today's class, wait a minute, I will share the PPT. Okay, can you see my slides?
Yes, sir.
Okay, fine. So what we'll do today is we'll learn how to apply the first law of thermodynamics to a closed system for various processes which are listed on the screen. So one by one we'll learn how to apply the first law for let us say the constant volume process, then the constant pressure process, the isothermal process, then the reversible adiabatic process or isentropic process, and at last the polytropic process, right? And law of the process is written in the bracket. For constant volume process, V is equal to constant is law of the process. Similarly, P is constant, T is constant, PV raised to gamma is constant, and PV raised to N is constant. So all these are nothing but the laws of those respective process, right? So let us take the first process, constant volume process. Now we'll learn how to apply the first law for this particular process. So draw this PV diagram quickly. So we have the initial state of our system, state 1, and this is the state 2. So what we have done here is at constant volume, the pressure of the system is reduced. So this volume V1 is equal to V2 is constant, right? And the initial pressure is P1, so the final pressure is P2. Now how to apply the first law for this? So first of all, find out what is the work done. So we know work done is in absence of any other work apart from PdV work, we calculate it using this expression. W is integral PdV. Now there is no change in volume, so it is 0. We know this, correct? Now the second part, find out what is the heat supplied for this process. So using the elemental approach now, I am writing this D cross Q is mCV dt. Now heat is supplied at constant volume, so that's why I'm writing mCV dt here, heat supplied. So if I integrate this expression, I can write the total heat Q supplied is mCV. For dt, I can write temperature difference T2 minus T1, final temperature minus initial temperature. So this is what the heat supplied at constant volume. Now moving further, you can apply the first law now. So I'm just using that expression Q is equal to delta E plus W. So when there is only internal energy, so if I'm neglecting the changes in kinetic energy and potential energy, this term I'm going to replace by delta U. So I'm using this form Q is equal to delta U plus W here. So same thing is written here. So Q is equal to W plus delta U is written as U2 minus U1. Right? Internal energy is property of the system, so I can write the definite value at state point 2 minus definite value at state point 1. So that's why U2 minus U1. So, and we know Q and W are not the point functions, they are path functions, right? So this Q I am just replacing by MCV T2 minus T1 here. Work is 0, we know this, so I am just putting it here, and just rewriting this expression, I can write this equation, right? Now moving further, so for this U2 minus U1, I am just writing delta U, change in internal energy is written as delta U. So delta U is nothing but MCV T2 minus T1, right? So in differential form, I can write du is equal to MCV dt, right? And from this, for a per unit mass basis, so this is the total internal energy, and small u is the energy per unit mass, U by M, right? So this is how, if I write du by M here, then that is nothing but the small du. So I can write du is Cv dt, and from this, the familiar expression which is known to us, we have seen this before. So Cv, or the specific heat at constant volume, is nothing but the rate of change of the specific internal energy with respect to the temperature, keeping volume constant. Correct? So note on this. And at last, for this process, constant volume process, what happens when you supply the heat? There is change in internal energy. So internal energy of the system will change. So depending on whether you are supplying heat to the system or taking the heat out of the system, there will be either increase or decrease in the internal energy of your system. So, but this thing is sure that Q is equal to delta U for a constant volume process. So you can look at this expression. So as W is 0, whatever heat is supplied will cause the change in internal energy of your system. So that's why Q is equal to delta U is the valid expression for constant volume process. Is it clear?
Yes, sir.
Okay, can I go to next slide now? Note on this. Now we will follow more or less the same steps for any other process, maybe constant pressure process or isothermal process. So these ABC 3 steps will follow more or less same steps. Fine. So moving to the next process, constant pressure process. Again, I have shown the PV diagram here. So this time this P1 is equal to P2 is P. The pressure is constant, and the volume of the system is changing from V1 to V2. So the expansion is taking place. Initial state is 1 and final state is 2, right? So we know how to find out this 1-2 or 1-2 or 1W2, one and the same. So I am using the same steps. So work done W is integral P dV. So P is taken out of the integral, reason being it is constant, and there is change in volume dV. So change in volume is V2 minus V1. So I am just rewriting this expression, and finally I can write work done as P2 V2 minus P1 V1. Or if I use the ideal gas expression, I can say P2 V2 is MRT2 and P1 V1 is MRT1. So in terms of temperature difference, the same expression can be written like this. So W is MRT2 minus T1, right? Now the second step, find out the heat supplied. So I am writing the differential equation in the differential form. D bar Q or D cross Q is MCP dt. Heat is supplied at constant pressure. So this is kept as it is MCP. If you integrate this, you will get this expression. Q is MCP T2 minus T1, right? So you can apply now the first law of thermodynamics for this process. So you can write Q is equal to delta U plus W. So the same expression, Q is delta U plus W. And for this, I am putting MCP T2 minus T1, right? And then W, we know just now we derived this expression MR T2 minus T1. And the change in internal energy is given by MCV T2 minus T1. We have seen this. The change in internal energy is nothing but the equal to the heat supplied at constant volume. We have seen this in the previous slide. So the same expression I'm just putting it here. And when you solve this, T2 minus T1 you can cancel out throughout the expression. Mass can be cancelled out throughout. And then what you get is this expression Cp minus Cv is equal to R. We know this. We have studied this in even physics also, that the Cp minus Cv is equal to R, where this R is nothing but the gas constant. We know this. Now, instead of writing this in temperature form, the same expression I am writing in different form, right? So you can write Q is equal to P2V2 minus P1V1, right? Plus U2 minus U1. So I'm just substituting this expression for the work in here. So Q is P2V2 minus P1V1 plus U2 minus U1 will remain as it is, right? Then I'm collecting the terms containing the suffix 2 together and suffix 1 together and writing this expression. So Q is in first bracket P2 V2 plus U2 minus P1 V1 plus U1. And we know this is nothing but the definition of the total enthalpy H. We know H is U plus PV. So this is H2 and this is H1. This is how Q is equal to H2 minus H1. So finally, what we conclude from this slide is Q is equal to delta H for constant pressure process. So in case of constant pressure process, when you supply the heat or when you extract the heat from the system, there will be change in the enthalpy of your system. Now, depending on whether heat is supplied to the system or taken out of the system, there will be either increase or decrease in the enthalpy of your system. But this expression is valid for the constant pressure process, that the heat supplied will cause the change in enthalpy of your system. So two things you should note down somewhere. From the previous slide, we concluded that the heat transfer or the heat supplied in case of constant volume process will cause the change in internal energy of the system, whereas the heat supplied in case of constant pressure process will cause the change in enthalpy of your system. Now, can I go to next slide?
Yes, sir.
Yes, sir.
Fine. Now, moving further, let us talk about the next process, which is isothermal process, constant temperature process. So again, I am taking the PV plane. I am showing the initial state 1, final state 2, and law of this process is PV is equal to constants, isothermal process. Fine. Then note down the pressure P1, P2 here, volume V1, V2. Again, I am following the same steps. So the work done, W is integral P dV. We have already derived this expression, so I will not talk more about this. So we know this, W is P1 V1, ln V2 by V1, and V2 by V1 can be replaced in terms of P1 by P2. So P1 V1 is P2 V2. So from this I can write V2 by V1 is P1 by P2. So this is how I am replacing this term, right? P1 by P2. So, and if I put P1 V1 equal to MRT1, the same expression I can write in this form. So just note down this expression for the work done. W is P1 V1 ln V2 by V1, or P1 V1 ln P1 by P2, or MRT1 ln P1 by P2. Now, second step. So let us find out what is the change in internal energy. Write down the expression for the change in internal energy. So we know the delta U, the change in internal energy, is nothing but the heat supplied mCv dt at constant volume. So I am just rewriting this expression, right? And as there is no change in temperature, it's an isothermal process, the temperature will remain same. So this delta T is 0, so I can write delta U is equal to 0. There is no change in internal energy in case of isothermal process, right? So this is part B. Now, if you apply the first law of thermodynamics, I am writing that expression, standard expression, Q is equal to delta U plus W here. And I already said that delta U is 0 for isothermal process. It means Q is equal to W for isothermal process. So that's why Q is equal to W is equal to the same expression I am writing it here. And you can use any of these forms here. Q is equal to W. So the thing which you should note down in case of in case of isothermal processes, there is no change in internal energy. Delta U is equal to 0. Note it down. There is no change in internal energy in case of isothermal process. and Q is equal to W. So the moment you know delta U is 0, we know this Q is equal to W for isothermal process. Now can I go to next slide?
Yes, sir.
Yes.
Now let us talk about the next process, which is reversible adiabatic process or isentropic process. Law of the process is P raised to gamma is equal to constant. Again, I am following the same steps. So work done is integral P dV. Again, just replace this P in terms of V because dV is there. So I have to evaluate integral with respect to V. So write P in terms of V. So the C can be taken out of the integral being constant, and once you solve this, we have already derived this equation. That work done in isentropic process or reversible adiabatic process is P1 V1 minus P2 V2 upon gamma minus 1. And if you replace this term in terms of temperatures, the same can be written in this form. So W is mR T1 minus T2 divided by gamma minus 1. Now part B, application of the first law of thermodynamics. So you can write Q is equal to delta U plus W, right? Same expression which we have been following throughout. Then we know for an adiabatic process, Q is 0. There is no heat transfer. Q is 0 for an adiabatic process. So I am just putting that value here. So W will remain as it is, and I'm writing U2 minus U1 as it is. So if you rewrite this expression, you can write W is equal to U1 minus U2. Or if I am writing delta U for U2 minus U1, I can write the expression like this. So delta U is equal to minus W in case of reversible adiabatic process. So note down this. So in magnitude, the change in internal energy is equal to the work done in case of reversible adiabatic process in magnitude, but the sense is opposite. Note it down. Hello.
Yes, sir.
Yes, sir.
Okay, fine. Now the last process. Let us look at the polytropic process. P raised to n is equal to constant. Now we know this work done in polytropic process can be written in this form in terms of pressure volume, and in this form in terms of temperatures T1 and T2. So write down those expressions. Now let us write down what is the change in internal energy. So this is base V, not here. So delta U, we know this is written as mCV dt. So mCV T2 minus T1. So application of the first law will give you, this is the standard expression, Q is delta U plus W. Now I am just substituting for these two terms. So Q will remain as it is, W is written in terms of temperature, so mR T1 minus T2 divided by n minus 1. And for delta U, I am writing this expression mCV T2 minus T1. So everything is in terms of the temperatures, right? So if you take, now this is important, if you take the second term common, means you have to take this term common and use Cp minus Cv equal to R, substitute Cp minus Cv equal to R, and this ratio of Cp by Cv as a gamma, right? The adiabatic index relation, then you will be in position to derive this equation. What you have to do, you have to take this term common from these two. This is first term and this is second. Take this term common and then use these two substitutions. Cp minus Cv is equal to R and Cp by Cv is equal to gamma. And the same expression can be converted in this form. So you will get Q is equal to mCv n minus gamma divided by n minus 1 into bracket T2 minus T1. So this is the expression for the heat transfer Q in case of polytropic process when temperatures T1 and T2 are known. So you should use this equation to find out the heat transfer. That's the idea behind deriving this equation. Now, second half, what you have to do is, instead of taking the second term common, this time you will take the first term common. So take the first term common and use again the same substitution. Cp minus Cv is equal to R and Cp by Cv is equal to gamma. And this equation will get transformed to this form now. So you can rewrite the expression and you will get Q is equal to gamma minus n divided by gamma minus 1 into mR T1 minus T2 divided by n minus 1. So make note that this mR T1 minus T2 by n minus 1 is nothing but the work done in polytropic process. So this is work done in polytropic process, this part, right? So I'm just writing the same expression here as Q is equal to gamma minus N divided by gamma minus 1 into work done in polytropic process. So if you have to find out what is the heat transfer in case of polytropic process, right? And if you know what is the work done, and you know the polytropic index N and the adiabatic index gamma, then straight away you can use this expression and find out what is the heat transfer in case of the polytropic process. So that's the idea behind deriving the second equation. Is it clear? Hello.
Yes, sir.
Okay, fine. Now this is important slide. We'll try to establish the relationship between these three most important variables, that is pressure, volume, and temperature. So we will try to write these PVT relations now, or PVT relationships, right? So I'm taking the polytropic process as a reference. However, same thing is applicable for the reversible adiabatic process as well, right? So I know this relation P1 V1 raised to n is equal to P2 V2 raised to n. So I am using the law of the process, PV raised to n is constant, right? So we know this for ideal gas, I can write P1 V1 is equal to mRT1. So similarly, I can write P2 V2 is mRT2, right? Now, when you use these two expressions, you can write or divide this by this. You can write T2 by T1 is P2 by P1 into V2 by V1, right? Now, so if you put this expression and write down this, or if you compare these two expressions, this one P1 V1 raised to n is P2 V2 raised to n. From that you can write this V2 by V1 is P1 by P2 raised to 1 upon n, right? And you write the reciprocal of this, which you can write P2 by P1 raised to minus 1 by n. Just index will be minus. I'm writing 1 upon this, so you can write it like this. So first relation you can note down is T2 by T1. This is one first relation you can note down. V2 by V1 is P1 by P2 raised to 1 upon n. And in terms of temperature ratios, if you put this expression here, that V2 by V1 in terms of P2 by P1 raised to minus 1 upon n here, then this expression will get transformed to this form. So T2 by T1 is P2 by P1 raised to n minus 1 upon n. Fine. This is important. So P2 by P1 is V1 by V2 raised to n. Now this is written using the same expression. So instead of writing this V2 by V1 ratio, I'm writing P2 by P1 ratio. So it is V1 by V2 raised to n. We know this. Now, instead of replacing this term, now this time you have to replace this P2 by P1 ratio here and write this right hand side in terms of the ratio, either V1 by V2 or V2 by V1. So you can write this as a minus 1, V1 by V2 raised to minus 1, and then put P2 by P1 as V1 by V2 raised to n here, and then you will get this expression. So T2 by T1 is V1 by V2 raised to n minus 1. So these three relations are important. So two are in terms of temperature, then these two are in terms of pressure ratio, and these two are in terms of the volume ratio. So this PVT relationships. So these expressions will be used while solving the problems. While solving numericals, these expressions are very important. So you note down this. Rather than memorizing those expressions, you should understand how they are derived. No? So if you remember only this part, now this equation, this is more than enough to derive these equations. So even if in examination, if you forget whether it is V1 by V2 or V2 by V1, you should be in position to quickly derive this and then use it. Is it clear?
Yes.
Now, so can I go to next slide now? Now it is time to apply whatever we have learned up till now. So take down the first numerical now. Let us go through the problem statement first and then draw the PV diagram. Don't jump directly to the PV diagram. So as shown in figure, a gas with a piston cylinder assembly undergoes a thermodynamic cycle consisting of three processes in series. Three processes are there in series. So process 1 to 2 is compression with U2 is equal to U1 means there is no change in internal energy. Delta U is 0, right? So what must be the kind of compression process then? 1 to 2. See, this is the compression process. Now why I'm going in this direction? Because it is compression. So the pressure should increase and volume should decrease, right? So that's why I'm taking point 1 first and then I'm going in this direction. So this is constant. This is compression with U2 is equal to U1 means delta U is equal to 0. Now what is the process for which change in internal energy is 0? The law of the process must be, this must be isothermal process or not?
Yes, yes, sir.
Okay, fine. So you reached to point 2 now. Now next, process 2 to 3 is constant volume cooling. So from this point you have to do constant volume cooling. So when cooling takes place, what should happen is the pressure should, hello, when volume remains constant volume cooling. So volume should remain constant. So what should happen then to pressure? Pressure should decrease, constant volume cooling. So that's why we are going in downward direction here, right? And volume is constant. So V2 is equal to V3 is this value, which is given. So this is step 2 or process 2 to 3. Now what is process 3 to 1? Now this is closing of your cycle. So it is constant pressure expansion with the work W31 as 10.5 kJ. So constant pressure expansion. When I say expansion, I should go in right hand side direction for expansion, and for compression I should go in this side, right? Get me or not? So I am saying constant pressure expansion, so I am going in this direction, and this is our final point. This is constant pressure process. So this is P1 is equal to P3 here. So whatever the pressure they have given, is it given or not? So this is given, P3 is equal to P1 is given here, right? And note down one more thing, they have given the work done in this process W31. So when you go from point 3 to point 1, the work done in this constant pressure expansion is given, which is 10.5 kJ. Note down the positive sign indicates this is the work done by this system. Now for the cycle, this value is given. W for a cycle is minus 8.3 kilojoule. There are no changes in kinetic energy and potential energy. It means when you write this total E is equal to EK plus EP plus U, these two are not there. So you can simply replace this E by EU, right? Determine, number 1, the volume at state 1 in meter cube. So you have to find out what is this volume V1 in meter cube. All units will be using SI units only, so it will be by default in meter cube. Then the work and heat transfer for process 1-2 each in kilojoule. So you have been asked to find out what is W1-2 and what is Q1-2. Clear? So this is what you are supposed to find out. Now if you have understood the analysis of the process, whatever the analysis we have done so far, you should be in position to solve this on your own. I need not have to explain how to solve this. Let us try. So first of all, you have to find out the volume at state point 1. So write down what is given and then start to solve. Hello. See, I have to find out volume V1. It means I have to look at either this process 3-1 or this process 1-2, right? Now apart from this constant pressure process, this value is given, pressure is known to me, right? And even the volume at point this is known, V3. So I can use this data to find out what is the volume at V1. One more additional data is given for process 3 to 1. What is that data? This work done in process 3 to 1 is known to me. Correct? So what you should do is work done in process 3-1 is
PD.
this 10.5 kilojoule, right? Correct. Now, how you write the expression for work done in constant pressure process? So it should
P
be
delta V.
so it is pressure into change in volume, no? So for process P3 321, I will write the pressure P3 into the change in volume. So change in volume is final volume is V1 minus initial volume is V3, right? Getting me or not?
Yes, sir.
So if I am taking this value in kilojoule, now remember this is important. If I am taking this value in kilojoule, I must take the pressure in kilopascal. Remember this. Then and then only this kilo will get cancelled out. Right? Otherwise,
Yes, sir.
I should take this value in joule and then the pressure in Newton per meter square. So right now I am taking it in kilopascal because I know this is also in kilojoule. So this is known, V1 is given, V3 is given, I can find out V1 from this. So find out V1.
0.103.
Okay, V1 is 0.103 meter cube. So I'll write it here only, 0.103 meter cube. Fine. Now next is you have to find out what is W1-2 and Q1-2. Now I will find out W1-2 and Q1-2. How will find out
So
W1-2?
W of cycle is W1-2 plus W2-3 plus
Very good. Very good. Very good. Name yourself.
Sanchit Patil.
Sanchit. W for a cycle is known to us. They have given, right? So this is W1-2 plus 2-3 plus 3-1. I can write it like this, no?
Constant volume W2-3 0.
So this is 0, right? And this is given. This is given. Correct? This is also given for cycle. So this is given. I have to find out W1-2. I can find out using this expression. Correct? The work done for a cycle is the summation of all the works in the process. So tell me, what is W1-2 now?
Minus 18.8 kilojoules.
Okay, minus 18.8 kilojoule is W1-2. Okay. Now find out Q1-2 then. I'm not going to find out. I'm going to directly write the answer. Why should I write directly the answer without solving?
So it's isothermal, so Q will be equal to W.
Or is it for a cycle? What is the situation for a cycle? Summation W of a cycle must be equal to summation Q of a cycle or not? Can I use that?
Yes, sir.
So you can use that. Summation W of a cycle must be equal to summation Q of a cycle or not? I can use this. So find out Q1-2. Now this side is known to me, that summation Q of a cycle is known. So you can write either the equation like Q1-2 plus Q2-3 plus Q3-1, right? Or you can simply write the expression for the process 1 to 2 like Q1-2 is delta U1-2 plus W1-2, one and the same. Correct? Or not? And U2 is equal to U1 is given to us. So we know this delta U1-2 is 0. Then this is 0. It means Q1-2 is equal to W1-2 or not. That's why I was saying without solving, I am going to write it. Have you understood this or not?
Yes, sir, understood.
Very good. So W1-2 and Q1-2 are one and the same because there is no change in internal energy of your system in process 1 to 2. So Q is equal to W for that process. Simple. So this is the final answer. 0.103, na? It was correct. This is minus 18.8, minus 18.8. Fine. Now, can I go to next slide? What is the time? Still, we have 25 minutes. No, a lot of time is there. We can solve one more numerical now. Should I go to next slide? Tell me quickly.
Yes, sir.
Yes, sir.
Fine. Now, moving further, we'll solve somewhat more complex problem now. Take down this. Now, what I expect from students is using this data, they should be in position to draw the PV diagram or TS diagram if required. They should be in position to show this schematically. And then only they'll be in position to solve. This is what I feel personally. See, if you know how to draw the PV diagram, your 50% job is done. And if you understand what is given, then 75% of your job is done. Then what remains is only 25% of calculation, nothing big in that. So take down 0.3 meter cube of air at 4-point bar and 140 degrees C is contained in a system. A reversible adiabatic expansion takes place until the pressure falls to 1.02 bar. The air is then heated. Now you should note down those keywords. This is the data given. This is a state point information. At state point, let us say 1. A reversible adiabatic expansion takes place. These are the keywords. Reversible adiabatic expansion. When I say reversible adiabatic, it means the law of the process is this, and expansion takes place. Now this word is important, expansion. So pressure should decrease and volume should increase. I should understand this. Takes place until the pressure falls to. So what is the pressure after expansion they have given? So this must be P2. Now the air is then heated at constant pressure. Now this is important. Heated, and this heating takes place at constant pressure till the enthalpy increases by 75 kilojoules. So this is change in enthalpy. There is increase in enthalpy. Means I should go from left to right in this process, heating process at constant pressure. I should go from left to right. Now calculate what you have to do. Calculate the work done and the index of expansion. So what is this index of expansion? Gamma, you have to find it. If the above process are replaced by a single reversible polytropic process. Now this you have to find out when you replace these two processes by a single process. So the index of expansion, if the above process are replaced by a single reversible polytropic process, means you have to find out N, polytropic process index N. When you replace these two processes, reversible adiabatic plus the constant pressure process by a single process, giving the same work, this is important, same work between the initial and the final states. Take Cp is equal to this, Cv is equal to this. Clear? So this is the data given data. Now I am just going to project how to draw the PV diagram on the screen. You just pay attention, and you should be in position to do the same thing even in examination. So this is the PV plane I am taking. Then I know this 0.3 meter cube volume is given. That's why I have shown this line first. 0.3 meter cube volume, and I know 4.5 bar pressure is given. So I know this point. So intersection of these two I am going to take. And I know the temperature at this point, that's why 140 degrees C I have written. So this is my state point 1. And look at the first process. I said reversible adiabatic expansion. So law of the process is P raised to gamma is equal to constant. Now why I am going in this direction? Because it is expansion. Clear? So this is my state point 2. Now what is given at state point 2? The pressure 1.02 bar. So I must project this point, this state point 2, project it here. So pressure is 1.02 bar. This is how you should note down the data in the same sequence, the way I am doing it here. Now second is, I have one more process here. The air is then heated at constant pressure. So when it is heated at constant pressure, I should go in right hand side direction. So I am going in right hand side direction. And this is constant pressure process, right? So this is my state point 3 now, right? Constant pressure process is 2 to 3. And what is happening in this process is there is increase in enthalpy of my system. So this delta H, right? Delta H for process 2 to 3, process 2 to 3, this is 75 kilojoule. That is what they have given, right? What you have to do first is calculate the work done. So we have two processes now, so you can find out what is work done in process 1-2 plus you can find out what is work done in process 2-3. So that will give you the total work done, correct? This is first part. Now what you have to do in second half is you have to replace these two processes by a single process like this. And what is that single process? Is a polytropic process. PV raised to n is equal to constant. Now why I am replacing this process from initial state and final state? Because they have said it that the initial and final states will remain one and the same. And how I should use this process is whatever the work done I am taking for the first case, sum of these two works, the same work should be there in this process. This is the condition. And under such condition, what is this index n? This is what they have asked. Is it clear? Hello. Yes. So can you solve this now? Or should I explain the procedure how to solve this and then you will solve it? Explain. Okay, I'll go to next slide and I'll explain how to do this. Now, the same diagram I have shown on the screen now. So these are the steps now. So look at the process 1 to 2. Now process 1 to 2 is P1 V1 raised to gamma is P2 V2 raised to gamma. Now I can find out what is gamma. So it is simply ratio of Cp by Cv. We know this. So Cp value is given, Cv is given. So can you find out gamma? Right? Then next, the moment you know gamma, further you can find out what is the gas constant R also, because Cp and Cv both are known to me. So I will find out what is gas constant R. Now I am using this relation, the same expression. P1 V1 raised to gamma is P2 V2 raised to gamma. From this I can write this V2 can be written as V1 into P1 by P2 raised to 1 upon gamma. Same, this expression is solved further. So I can write this V2 by V1 raised to gamma is P1 by P2, right? And then this V2 is written as this V1 into P1 by P2 raised to this raised to 1 upon gamma. This is how I am writing this equation. So I know what is volume V1, I know pressure P1, pressure P2, right? So I can find out volume V2 from this, correct? Now once I know the volume V2, I will go further and find out what is the temperature T2 here. So I know how to write down the ratio, temperature ratio T2 by T1 is P2 by P1 raised to gamma minus 1 upon gamma. We have derived this previously. Only it was in terms of n minus 1 upon n. So n is replaced by gamma only. So the same expression is valid for this process as well. So I can write T2 is equal to T1 into P2 by P1 raised to gamma minus 1 upon gamma. Now T1 is known to me. Note down that temperature should be taken in Kelvin. So convert these temperatures in Kelvin. Then add just 273 to this. Then T1 is P2 by P1 is known, gamma is known, so I can find out T2 from this. Of course, this will be in Kelvin here, right? Now I can use the equation PV is equal to MRT. So I'm applying this at state point 1, so I can write M is P1 V1 upon RT1. Now at state point 2, I know the pressure P1, volume V1, R gas constant. Just now I calculated, temperature T1 is known to me. So I will find out what is the mass of the gas. So find M. Clear? Next. Now I am going to the next process 2 to 3 now. See, when I'm switching to next process 2 to 3, when I know what is pressure, volume, temperature at point 1 and what is the pressure, volume, temperature at state point 2. Now, the moment I know these three quantities at any state point, I should go to the next process because I can use that data for the further analysis. That's the idea behind. So I am switching to the process 2 to 3. So I know this is constant pressure process, P2 is equal to P3. So I am using this expression which we have already derived for what is the heat transfer in case of constant pressure process. It is mCp dt, we know this. So I am writing Q2-3 is mCp delta T, which is nothing but mCp T3 minus T2, final temperature minus initial temperature. We are going in this direction, right? So using this expression, I can find out what is the temperature T3 now. Get me or not? Now, why I can do this? What is Q23, 2-3? Hello.
Sir, what?
What is Q2-3? Q2-3. What is this Q? Heat transfer in case of constant pressure processes. Is it change in enthalpy or not? Go back to the slides where we have applied first law.
Yes.
So the heat transfer in case of constant pressure process will cause change in enthalpy, and this delta H is given for the process 2 to 3 or not. So delta H for process 2 to 3 is known to us, something around 75 kilojoule they have given, right? So it means in this expression Q2-3 is known to me. So this side is known, M is known, Cp is known, T2 I calculated. So from this I can find out what is T3. Clear? Hello?
Yes, sir.
Okay.
Yes, sir.
So at point 3, I know the pressure P3, temperature T3. Now only what is remaining is volume V3, right? So find out volume V3. Now how to find out volume V3? So I can simply use the relationship like P2 V2 is equal to MRT2, P3 V3 is equal to MRT3, and just take the ratio. And I can write the expression like this. So V2 by V1 is V3 by T3 for this process. Are you getting how I am writing this expression, or should I write it here?
No, sir.
Okay. So now from this expression we know this volume V2 is known to you, right? Because you have calculated it here. So volume V2 is known, temperature T2 you have calculated, the temperature T3 just now you found. Then find out volume V3 using this expression. Now you know volume V3 also. So you know PVT at all these state points. This is more than enough for calculating whatever they have asked. Now find out the work done in process 1, 2, 3. So you can divide it as process 1-2 plus process 2-3. So I'm writing W1-2 plus W2-3. So for this, we know that the work done in isentropic process or reversible adiabatic process is given by this expression P1 V1 minus P2 V2 upon gamma minus 1. Or you can write MR T1 minus T2 upon gamma minus 1 also, that's fine, plus P2 into V3 minus V2. So this is the work done in process 2-3, P delta V, right? Or you can write it in terms of this temperature also. You can write MR into bracket T3 minus T2, right? And this will give you the total work, right? So this is total work 1-2-3. Now what you have to do is work done by the polytropic process, which you are replacing these two processes by a polytropic process. So the work done in this process must be same. So that's why this W1-3 is equal to 1-2 plus 2-3. So this same I am taking it here, which you have found here. So just put it here. And now you can write what is W1-3. So you know W1-3 for a polytropic process is given by this expression P1 V1 minus P2 P1 V1 minus you can write it as P3 V3, but P2 is equal to P3. Otherwise you write it as P3 only. P2 is equal to P3. So P1 V1 minus P3 V3 divided by N minus 1. Now this side is known, right? I know P1 V1, I know P3 V3. Only unknown is index N. So this is how you will find out index N. So that's how you are supposed to solve this problem. Is it clear? Hello.
Yes, sir.
Okay, solve it. And should I project the answer on the screen now? So here is the answer. You can cross check your answers with what is projected on the screen. I may be wrong.
Sir, can you show the question once?
I should go back now. Volume V1 is 0.3. Drishti is asking for value of V1, right? Drishti? Hello. Got it, no? Okay, fine. Now, should I go to next slide or?
Yes, sir.
Okay, because you need this procedure, entire procedure, no? How to solve. See, each and every step here is essential. You cannot skip the part in between. And the sequence is also justified why we should go in this particular sequence only. Why we should go from point 1 to point 2 and then from point 2 to point 3. So if you solve the problem in logical sequence, no, it is not difficult. And if you do not know the steps, then you will just keep on moving from point 2 to point 3, then from point 3 to point 1. And this is how you will go round and round, and at the end, you will not be in position to solve it. So this is what happens with the students, those who do not have the proper the procedure and the proper understanding of how to solve it, they will just keep on revolving. Okay, now again Drishti wants me to go back and show the question slide. Just take down the snapshot of this slide, so that you can refer it while solving the problem. See, whatever data is given, all the data is noted in the diagram also, on the next slide. Cp value is 1 kilojoule per kgk and Cv is 0.714. Or more precise values you can have is Cp is 1.005. And I should erase this. See, in last problem we talked about a very simple cycle, and a lot of data was given there. Then we started with the two process like this, 1 to 2, 2 to 3, and these two processes were replaced by a single process. The next type of problem will be the complete cycle. So write this as P3 only, and don't write P2. P3, V3, that's fine. Okay, all of you, are you getting the value of gamma as 1.4?
Yes, sir.
Correct?
Yes, sir.
Okay. What about volume V2? Is it 0.866?
Yes, sir.
Yes, sir.
Very good. Temperature T2?
Yes, sir.
sir.
270.256. I kept it for 3 decimals.
That's fine. See, there can be slight variation in these values. That is accepted. Mass?
It's the same.
Very good. Temperature T3?
335.873.
That's fine. I rounded it off to 2 decimal places. Then volume V3?
So 1.076. Same.
That's fine. Again, I rounded it off to 2 decimal places. And
No,
the work done?
I'm finding out. Find it out. Sir.
Okay, find out. In examination, you should try to cross check also. So instead of writing this expression in terms of the pressure, use this kind of expression also. Mr T1 minus T2 by gamma minus 1 plus this you can write as Mr T3 minus T2, this part. Still you will get the more or less the similar kind of answer or same value of the work if you use the expression in terms of temperature differences. Now, if you do this in examination, you need not have to wait for examiner to evaluate whether your calculations are correct or not. Well in advance, you know whether it is correct or not because you cross-checked it. Is it 138.5 kilojoule?
Sir, I'm getting 138.09.
Yeah, that's fine. Now, one more thing I forgot to explain here is, see, everywhere we are using pressure in kilopascal. That's why your answer is in kilojoule. Note down this. Why this kilojoule is, when you write the product PV, pressure is used in kilo. The volume is in meter cube everywhere, but the pressure is in kilopascal. That's why your answer, this answer is in kilojoule. By chance, if you use this value in Newton per meter square, your answer will be in joule. Make note of this. So your answer is 138.0?
09, sir.
Yeah, that's fine.
Yes.
138.1 you can say, no?
Yes, sir.
That's fine. Find out n. Now put that value here and find out this index n.
Sir, 1.18.
Correct. The same value I have written on the screen, 1.18. So I think we should stop now. That's all for today's class.